This is the MAT140 lesson number 5 on polynomials and yield to maturity. The following formula relates a bond's price, its current market value or present value, with its future earnings. So we have the current price of the bond is equal to some future, like let's say a series of terms which involve cash flows and this yield that is a interest rate, a growth rate or rate of return. And so this is a formula that we could use sort of generally for calculating bond prices. This is from a website, investopedia.com. Here's the link. You can Google that to look this up to see how it's written in that context. That's the website where I got the idea for this particular lesson and how it could relate to polynomials. So actually what we have here, and when I write it this way, it's not really a polynomial in this form, but when I choose to solve for r, I will write a polynomial, and that's where the polynomial comes up. So we can write this formula in this form, where we have the following variables defined, where P is that current market price, the bond price in the formula above. P is the bond price. It's what you would pay today for the bond. C is what's called the coupon value. It's these regular payments that you get from the bond. And to simplify, I'm going to assume annual payments. So they are based on the coupon rate that would be given with the bond and its face value. B is that face value. It's also called the par value. R is the yield, which isn't the same as the coupon rate. It changes as the current price of the bond changes. As its market price changes, its yield to maturity changes. And that's basically what we're going to be calculating. What is the yield to maturity? And to solve that, you can see it related to a polynomial. Really, of course, nobody who uses these would ever sit down with paper and pencil and solve a polynomial equation. But I think it's a really good education to see the background of these formulas that the computer is using. So anybody doing this in real practice would be using a computer, perhaps Excel or some other website online, to determine the yield to maturity. And so, of course, what I'm doing isn't job training, and that if you were to have a job like that, it's more of the mathematical background behind the formulas that are, give us these instant answers. And so you can sort of see the math behind them, right? So then n is the number of years until the maturity. So in this lesson, we'll look at calculating the yield to maturity when given a bond's present value P, its face value B, when we know the interest payments C, which are regular payments that are all the same, and that time to maturity N. And to simplify, we're only assuming annual interest payments. So the first example here, a $100 bond with a 3-year maturity has a coupon rate of 4% and a present market value of $94.65. So what is the yield to maturity? Okay, so I think a good way to approach this would be to go back to this formula to begin with. And let me just copy it here. Now, what values do we know at this point? We know the present value. Present value is P. So that's $94.65. Now we need to know what these coupon payments are, but they are based on this rate 4%. So what the C is the interest payment based on the par value or the face value. So there'll be $4 payments every year. That doesn't sound like a whole lot, but maybe you could buy a couple thousand of these. So coupon payment, our interest payment of $4. We're solving for the yield to maturity. So we don't know R. There's another $4 payment. And since it's 3 years, we'll just end with 4 plus the face value over 1 plus the yield to maturity raised to a power 3. what we're really doing is looking at the present value of all these future payments. This is a 1 year out payment of $4 1 year from now. This is a payment of $4 2 years from now. And this is the $100 face value plus that last interest payment, all received 3 years. And so we're just calculating what its present value is. And it's the sum of these three present values that add up to the total present value. To solve for r, the first thing I'll do is just convenience. I'll just make x this value 1 plus r, and then at the very end, I'll just remember to subtract 1. So it's just a little more convenient for writing it by hand rather than writing 1 plus r over and over. Let's just say x is 1 plus r. We'll solve for x, and then we just subtract 1. Well, at this point, what we need to do is, solving for x, we could multiply both sides by a common denominator, which is x cubed. So I have 9465 x cubed equal to, this would be 4x squared plus 4x plus 104. Now to solve this, what we could do is move everything over to one side and write it like that. Now here is a polynomial equation. This is a degree 3 polynomial equation. And generally, if it's degree 3 or higher, it's pretty difficult to solve in general. Some of the things you do in the pre-calculus class is learn factoring methods. That might be something you could approach this using a method of factoring. And there is one formula to solve and get exact values, but it's pretty complicated. And degree 4, there would actually be one formula that similar to the quadratic formula for degree 3 and degree 4, but it's amazing. It can be proven mathematically that once you hit degree 5, there is no one single formula to find all solutions, which is pretty striking that even just degree 5, and it's mathematically impossible to get exact solutions for every degree 5 from one formula only. So that's pretty significant general mathematical theory, but to solve a degree 3 or anything higher, absolutely, we can use the calculator or we can use the computer. If this was something on a test, would definitely have to be the calculator that you would use. But since this can also might be an assignment that you're doing at home, you can use the computer, and I'll do it both ways. So let's start with the computer because it's quicker and faster and easier to see, I think, on the computer. So how do we go about solving this? Let's go to Desmos again and get a graph of this polynomial. Okay, so here I am in Desmos, and I want to type in that equation, 94.65 x to the power 3. This is the shape of a cubic in general, if it's just degree 3. And then we have a minus 4x to the power 2, minus 4x, minus 104. So now, generally, let me back up a little bit. This is the shape of a degree 3, and you can see there's actually 3 solutions for this one. Generally, whatever the degree of the polynomial is, if you look at the highest power, that's how many solutions there are at most, up to 3 solutions. There could be 1, 2, or 3 solutions. And if it was a degree 5, there could be 1 or 2 or 3 up to 5 solutions. So it tells you the maximum number of possible solutions. Now, in the context of finding yield to maturity, we would expect something between 0 and 1, where 1 would actually really represent like 100% interest. So it's, in practical terms, probably something very close to 1 that is our solution. And probably just a little bit above 1 because we're going to expect some kind of positive interest rate. Maybe something between 0 and maybe 10% or something like that. So just because of the context and what of the question of the algebra question that we're solving, we can sort of look for solutions that are around 1 point something. So because as soon as I type in this, right, I don't see the entire graph, and that's a whole nother discussion to try to understand the general shape and all the solutions. But I'm specifically looking for a solution around 1, and I can see it right there in the graph. So I'm going to zoom in on that. It's an intercept. It's a point where the graph crosses the x-axis, and so it's a point that makes this expression equal to 0. So by graphing the polynomial and looking for an intercept, right there I could just point to it and see 1.06. That's the value of x. So I used the computer this time, uh, and now there could be 3 solutions, but the one that really matters in this case is the one that is close to 1. I get 1.06 from Desmos. Okay, we could do the same thing on a calculator. So let's go back to this same degree 3 polynomial. Use a calculator to find a solution. So what we could do is start off with, it was 94.65 x to a power 3 minus 4x squared minus 4x minus 104. And we're looking for intercepts for that. So let's think about what's an appropriate window. So we could go from 0, let's say you go from 0 to 2, because since we're actually solving first for x, whatever solution we'll have to subtract 1 from it. So somewhere between 0 and 2, that would be between 0 and 100% interest. So 0 to 2 is a good window. That would capture anything really that's realistic for solution for yield to maturity. The x scale here, this is 0.1, so that seems fine. It doesn't really matter what you have there. And then even really the y scale, for the purpose of this particular process of trying to solve an equation, it doesn't really matter what you have for the y scale either. Okay, so then now obviously I've got a graph there where the polynomial is going, but it's such a steep polynomial at that value of x that it looks like a straight line. It actually really isn't a straight vertical line, but on the scale that we are looking at, you can't tell that if you moved over just a little bit, um, it increases with each increase in the value of x. You can't tell that from the graph, but that's actually what's happening. It's just not apparent. All that we really need to do is figure out what is this point where it's actually crossing. What is that point right there? So you can do it, really best way I think with the calculator would be to find an intercept. So that would be, if you see right above the trace, rather than doing trace, because that won't necessarily allow us to get right on that value. We'll use this, it says calc right above it in blue. So go second, calc, and then a 0. What we're looking for is a 0 of the function. So let's put 2. And then a left bound. Well, you could put 0 as the left bound. Anything less, let's put 0. And then a right bound, let's put 2. And then the guess, well, this is about right in the middle because I had a window from 0 to 2. So this, I'm going to guess it's about 1. Right? Guess 1. So there it is, 1.06. Actually, this is a little bit more accurate, perhaps, possibly, than the value that I was getting from Desmos. It's also possible that there's a little bit of error in the calculation as the calculator does it. So anyway, we're going to round off to maybe 2 places. So let's say 1.06, clearly the same answer I got from Desmos. Yeah, the thing is, I actually kind of trust Desmos a little bit more with this. I think the calculator may actually build up some error, and that's maybe what that is. Again, this is all sort of a numerical thing that I'm really trusting the computer or the calculator to find it, because it is generally very difficult to solve degree 3 and higher. Um, and so that's a whole nother topic. It's a pre-calc topic. And uh, yeah, so we can get some practical solutions using the practical tools of the calculator and the computer. Round off the two places there, 1.06, that's my answer. 1.06 is what I got from Desmos. All right, and then since the solution was 1.06, and I know that x was 1 plus r, so 1.06 is 1 plus r. That means the actual yield to maturity is 0.066%. That's the answer. Remember that if you put this in terms of x to get the polynomial easier to type in, then the actual solution for x is the yield to maturity plus 1. So just take off 1 and you've got the answer. By the way, another thing we could do is just check this. Here's a calculator on Investopedia, the website, and I could check it this way. I could say $100 par value, market value I had is 94.65. That's the purchase price of the bond. Annual rate, the coupon rate, 4%, and 3 years to maturity. Make sure you have it set on annually and calculate. It tells me yield to maturity is 6%. Gives you some explanation as to what that means. So we could check all of them with this, of course. This is more practical if you were really doing these for a financial reason. Uh, but I'm trying to give some math that might, is part of the answer behind where does it get that 6%? Where does that come from? And putting in the context of polynomials. And so, yeah, that's what we just did. Let's do another one. Another $100 bond, that's its face value, with another 3-year maturity, has a coupon rate 4%, the same as before, but the present value is exactly $100. So the present market value of $100, what would be the yield to maturity there? Present value 100, coupon rates are the same. I'm going to just write x instead of 1 plus r. We can multiply both sides by x cubed and move everything to one side. So it looks like that. And then of course, this one is what you would solve uh, using either the computer if you're doing this as an assignment at home, or on the calculator if you're doing this on an exam at the testing center. So either way, you just type this into the calculator and find the zero, or type it into Desmos or some graphing calculator and find the zero that way. So let's do it both again. So on Desmos, what does it look like? Actually, the equation, the only thing that changed was that uh, present value. The actual market price of the bond went to 100 So that's exactly the same. Everything else is exactly the same. This is the polynomial that I'm trying to solve. I want to know when that's equal to 0, right? 100x cubed minus 4x squared minus 4x minus 104. I want to know when that's equal to 0. So what I do is graph that polynomial and just look for the intercept. It's 1.04. Now, maybe zooming in a little bit, you can get a more accurate value. I still have 1.04 here, so that's my solution for the x, 1.04. So solving that degree 3 on Desmos, I found an intercept around 1.04. Solving on the calculator, it would look like this. Everything would be the same, it's just that first term, so let's just change that. It has a coefficient of 100. And I'm looking for that x-intercept. So, and this, I know I had the window set from 0 to 2, and this is counting by 0.1, so that's 10%, 20%, 30, 40, 50. It's like 0.5, 6, 7, 8, 9. That would be 1. So this is just after 1. So we need to, so if we're going to do a calculation to find the 0, we'll go to number 2. Left bound, we could go with 0 again, or just something less than 1. Right? So how about 0.5 this time? An upper bound, I know that was about 1, so I could just, as long as you guess something a little bit more than, well, it seemed to be, now it's kind of blocked out by the number here, but so, how about just 2? Because I know that is a right bound, so I'll type in 2, and that's the right bound. And then the guess, I know it's around 1, just a little bit more than 1, so I'm going to put in 1 as the guess, right, on the calculator. I wouldn't know yet. I know it's 1.06 from Desmos, but I'm sorry. I mean, I get 1.04 from Desmos. We got 1.04 with Desmos or calculator. So the yield to maturity is 4%. Actually, if you knew some finance, you might have been able to guess that 4% from the very beginning when I had the um, face value and market value equal. When that happens, the yield to maturity is actually going to be exactly the same as the coupon rate. All right, so let's move on to example 3. We're back again with a $100 face value on the bond, 3-year maturity. As before, the coupon rate is 4%. That means they're paying us 4% a year on the face value. But this one is selling at $105.77. Why would somebody pay extra $105 when they're only going to, its face value is only 100? Well, first of all, um, if you notice that you get $4 every year, you're going to get plus for 3 years. That means you're actually going to get $12 plus the $100 back. So you still might be willing to pay $105 for that. Um, and this would be something that was referred to as a premium bond because it's with a low rate of return. Um, it's going to be less than this coupon rate, but that's because it's pretty secure. You're very confident it's a highly rated company or a highly rated um, municipal bond where you can expect that you will definitely get that money, and so you have to pay a little bit more, and you're getting a little bit lower rate because there's very little risk involved. So I can actually expect that my yield to maturity will be lower than that coupon rate because I'm paying a premium on the bond, right? So let's set it up again. This is another one that's 3 years. Value of the bond right now is 105.77. The coupon value is $4 because that's 4% of the bond's face value. So that's $4. And I'm going to just call that X so I don't have to keep writing 1 plus R, and I'll just get the R at the end. Another $4 payment, X squared. And then the final payment is you get the interest in the final year plus you get the face value back. So that's $104. That's over x cubed. So we're solving for x. Once we have x, then we can figure out what the yield to maturity is by just subtracting 1. Multiply both sides by x cubed. Bring everything onto one side of the equation so that we can write this in terms of finding the zeros of a polynomial. So find the x value that makes that polynomial 0. So let's go to either calculator or Desmos. The only thing that changed in this example was it's now market value is 105.77. So if I'm trying to figure out where that's crossing, looks like 2% at 1.02. So 1.02 is my solution. So yeah, the yield to maturity is lower than the coupon rate. It's 2%. It would be lower interest rate on the yield and a higher price as its present market value because it has this This higher price is associated with a premium bond that is low risk, but those low risk bonds are giving you lower yield to maturity because what happens is that the riskier ones have to pay a higher rate. If this were a premium bond, it would be correspond to some low risk investment and therefore produces it corresponds to a low yield, a lower yield, and overall a higher market price. We could check that also with the calculator on Investopedia. So if I went to 105.77 was the market value with the annual rate, the coupon rate, the same and the par value the same, 3-year maturity the same. So now we're down to a 2% yield to maturity. Okay, now let's move to another one with a different par value, $1,000 face value on the bond. It's a 5-year maturity, coupon rate 6%, so they're paying us 6% a year off of the face value, and it is a discount bond. Its market value is less than its face value, 987.25. Let's figure out what is the yield to maturity on this bond. It's a series of interest payments that we compute their present value of all of those future interest payments for each year. Now this is 5 years. And in the last year, you get an interest and you get back the face value. So the present value, since it's selling for $987.25, and we know what all of these fixed guaranteed payments are as long as the payments are made on a regular basis at the same amount as they are promised according to the terms of the bond. So let's see, those are all going to be 6%. So I need to figure out 6% of the $1,000. This is the regular coupon payment. So that's actually $60. So $60 payment. And this is a place where it's just easier to go just to X. Right? We'll solve for R after we get the value of X. So these $60 payments every year, we're computing their present value and setting it equal to what the total present value is. And that's the face value, 1,000 plus 60. Oops. Now we can multiply both sides by X to the 5th. That's the common denominator. To solve an equation like that, generally very difficult. That's why we're using the computer or a calculator to find the intercepts. And in the context, we know the solution should be close to 1 so that we can sort of zoom in on that part of the graph to look for where it crosses. So let's write it equal to 0 so that we're actually looking for place an x value where the function 0, that is to say we're looking for the intercept. So the question is, what value of x do you get for that polynomial equation, degree 5 polynomial? So we'll go to the Desmos. I'm looking for 987.25 x to the power 5, and then all of these regular payments of $60. If I start with a window like this, it's kind of nice. You can sort of see the polynomial appear as I'm typing it in, which I think is kind of cool. So I was looking at 987.25 x to the power 5. And then a whole bunch of payments of $60 every year. Okay, so what's the intercept there? So if I get about 1.063, let's see if we can get a little bit more accurate value. 1.0631 if you zoom in on it. Okay, so 1.0631. Knowing that even though there are theoretically 5 possible different real solutions, the one that's most practical is the one that is close to 1, which I can zoom in around that area in the graph. And so that means the actual yield to maturity is 1.0631 minus 1. So that is to say, it's just the part that's above 1. So 0.0631, 6.31%. Okay, let's check it with the Investopedia site. So $1,000 par value, market value 987.25. Annual rate was 6%, and it's 5 years to maturity. Annual payments 6.31%. That's it. On the calculator, I need to type in a degree 5 polynomial. And I'm looking for a solution that I expect to be close to 1, so that the yield to maturity is some value, some percentage above, between 0 and 100% in the yield to maturity, and therefore the solution for x should be somewhere between 0 and 2. Right? So my window is set appropriately 0 to 2. So again, it's really a curve, but it's such a steep curve at these values that you really can't see the fact that it's curving. And I know this is 0.1, 0.2, 0.3, 0.4, 0.5, 6, 7, 8, 9. This is 1. So the solution is between 1 and 1.10. So it's something, maybe 6%, something like that, between 1 and 1.10. So we could actually even use that as our lower and upper bounds. Although, then I'd have to guess something between that. So how about I guess I start with 0.9 and use 1.1 as the right bound and then guess 1. Right? So I want to find a 0. So I'll do second, calc, number 2. You could just go 0 and 2 as your left and right bounds because they clearly are left and right bounds. Or you could be a little bit more creative. Okay, forget being creative. Let's just put in 0 and the right bound 2 because that's the right side of the screen, and then the guess is around 1. So 1.06305, which I'd round off to 0.631. So that makes me wonder, if this is indeed perhaps a little bit more accurate than what we were finding on Desmos and even on that Investopedia site. So let's round off to agree with the other ones. 1.0631 is the solution. And in doing that, you'll get that same answer. Yield to maturity, 6.31%. So let's look at a last example here. A $1,000 bond, 5-year maturity, coupon rate 6%. The present value is $1,050. What is the yield to maturity? So with the examples that we just did, we can just change a few values. In fact, all I have to do is put in a different market price. Adjusting the market price just means this coefficient right there, make it 1050, and everything else is the same. So I want to know the solution now. Looks like 1.0485, 0485. Looking at this particular example, I realized I could just take the example that I just did before and just switch out the leading coefficient because that is the market price. Make that 1050. Solve that, of course, using a calculator or a computer, and I got 1.0485 if I remember right. Let's check that. 1.0485, that's it. On the calculator, it just means deleting out this and then inserting a different value, 1050, and then do second calc. Let's find a 0, left bound 0, right bound 2, somewhere between there, it's around 1, 1.0485 if you round off to 2 places after the decimal in the percentage. So I get the same answer there, and one other place we could check it. So market value is 1,050, same annual rate, 5 years, annual payments, 4.85%. That's good. That's it. That's what I uh, found it to be in the process of solving a polynomial. Of course, I was still using the calculator or a computer to solve the polynomial because it's a degree 5 polynomial. Those could be really difficult in general to solve, but there's a little bit of the math behind how polynomials are related to this financial calculation. Okay, so with that solution, the actual rate is the 1.0485 that we got for x minus 1, so 4.85% yield to maturity. That's it. Okay, that's the end of the video. Hope it was helpful.